So in this question, everything is the same. You may use the same formula except for the standard deviation. So because the underlying distribution is a binary distribution, so you have to use the standard deviation formula from the binary distribution chapter. So remember, this is the standard deviation. And additionally, you have to remember that the standard deviation is determined by the null hypothesis. Then you have to use the null hypothesis when you calculate the standard deviation. So when the null hypothesis is true, standard deviation equals 0.5. So then it's easy, simple, and alpha is 10%, which implies 1.64. Then the belief is 50%, z value is 1.64, standard deviation is 0.5, sample size is 100. Plug in the numbers and you get these. And then given these critical values, your data says you found 42 out of 100. So 42% was the observed proportion. Then given the sample, can you reject the null hypothesis? Given the critical values, you may compare the critical values to the sample mean, and you can determine whether you reject or not. 3, 2, 1. So the lower critical value is 41.8%. But your observation is 42%. So therefore, 42%, your observation is within the critical values. It's from 41 point something to 58 point something. So 42% is clearly, like here, inside, slightly inside the lower critical value. So you do not reject H0. So 42% is close enough to your belief, 50%. Okay, now then, let's think about this. 42% is within the critical values, but it's you think it could be wrong. So you would like to check the potential error probability in this case. So if your decision was an error, what kind of error could it be? Can it be? If it was an error, what kind of error is it? 3, 2, 1. So the key point here is you could not reject H0. So you could not reject H0 if this decision was if this decision was an error, that means H0 is actually wrong, but you did not reject it. That's the only error you can think of in this case. Like once you don't reject something, once you don't reject the null hypothesis, then the only possible error is type 2 error. Type 1 error happens when you reject. Type 2 error happens when you don't reject. So here, you have to worry about type 2 error if your decision was type 2 error. Of course, you don't know if it's an error or not because to calculate to know whether it is an error or not, you have to know the truth, right? Otherwise, what you can do here is just make a decision and calculate the probability of that error, right? So that this is what I explained. So here I would like to calculate. I'm worried about my mistake, my error in the decision in the hypothesis testing. So I would like to calculate the type 2 error probability at 10%. That's the significance level I used. And I am going to assume that the truth is 42% because this is what I observed from the data. Just to assume. It doesn't need to be 42%. But in this example, let's think about this case. So the truth could be 42%. So I observed 42%, but by a random error, I may not be able to reject the null hypothesis, and I'm sticking to a wrong hypothesis. That was possible. So anyhow, if you assume p equals to 0.42, you may calculate type 2 error probability in this way. Type 2 error probability is the probability that you do not reject the null hypothesis, conditional on the assumption that p is different from 50%, specifically 42% in this case. And now non-rejection happens when x bar lies between the critical values. By the way, in this example, your observed x bar does not play any role. So x bar here is not your observation from this. It's not related to your data. It is just an unrealized variable, or just a distribution. If you could resample the data and redo the same hypothesis testing, then what would be the probability of type 2 error? That's what we are calculating. So x bar here has nothing to do with a specific number, 0.42. So next step is obviously a standardization using this value. By the way, another tricky point here is that because the assumption is 0.42, you have to utilize this for standardization. But in this standardization, the assumption also determines the standard deviation, because it is a binary distribution. X itself was binary distribution. So if you believe p is 0.42, standard deviation should be approximately 0.49, calculated by this. So using this standard deviation, you have to standardize x bar, right? So subtract the mean. Mean is also determined by your assumption, and standard deviation is also determined by your assumption. That's the major difference in the binary distribution example. Then from here, it's simple algebra. Calculate this part, minus 0.04, this part 3.31, and if you look up the cumulative probability for this value, you are going to get this one. And when you look up for minus 0.04, you'll get this one. So the difference is about 51.548%, which means you could not reject your null hypothesis, but you are now worried about if it is a type 2 error. We just calculated the probability of type 2 error. In that situation, you may make a type 2 error with 51%. Even though it is greater than 50%, it does not mean you have to change your decision. Given the hypothesis, and given the data, you could not reject the null hypothesis. That's it, but what it says is just use some caution. It's not always true. So even though the null hypothesis was not rejected, still it may be questionable. It may be wrong with some probability. Now what I'm going to do here is I am going to change the sample size. I want to see what happens when you increase the sample size to 400. Everything else being the same, I'm going to calculate type 2 error probability, and the hypothesis the same, significance level the same, everything being the same. And by the way, when you change the sample size, do critical values change? 3, 2, 1. Of course, the answer is yes, because critical values, where is that? Critical values have sample size in its formula. So obviously, you have to recalculate the critical values. Critical values are given by this. Now then, calculate the type 2 error probability by yourself. Using the new critical values, using the new sample size, and under the assumption that p equals to 42%, calculate the probability. Pause the video here. 3, 2, 1. Type 2 error probability is written in this way. You don't reject H0 under the assumption that the truth was 42%, and non-rejection happens when in this case where these two numbers are the critical values, and then standardize X bar. And remember, standardization uses the assumption 42%. It's mean, and also it determines the standard deviation. So standard deviation was approximately 0.49. Then if you do the math, do the algebra, you are going to get 5.592%. So it's a surprising number because previously in the same situation, type 2 error probability was 51%, greater than 51%. Type 2 error probability given the same situation, 51%, but now it is only 5%, only less than 6%. So it shows the power of sample size. So as you have more sample, larger sample, your analysis will be more accurate. Obviously, you have more information, so you can do better job in inference, statistical inference. So it reduces the error probability. So that's also an intuitive result from a larger sample size. Okay, this is what I prepared for today, and the next slide is a totally different topic, so I'm going to continue that on Thursday. So and okay, thank you for watching the videos, and see you on Thursday. Have a nice day. Bye.